All right, let's get straight into it. Welcome everyone to this high-speed, high-yield explainer designed specifically to help you absolutely crush the communication systems portion of your upcoming competitive exams. Whether you're gearing up for GATE, ESE, ISRO, or DCIO technical exams, you already know this subject is essentially a minefield of dense formulas and conceptual traps. Today we're stepping in as your expert mentors to cut right through that noise. We're going to zero in on the exact concepts, those sweet numerical shortcuts, and the classic pitfalls you need to dodge to secure your rank. I absolutely love this intuition-building analogy. Think of your baseband message, like a standard human voice, as a slow, heavy pedestrian. It literally cannot travel far on its own over the airwaves. It just doesn't have the energy. On the flip side, you have a high-frequency carrier wave. That's your express train, flying along at millions of cycles per second. Modulation is simply the process of buying a ticket and putting that pedestrian onto the train. We're letting our slow, everyday message reshape some physical property of that lightning-fast carrier wave.
So, pro tip for your technical interviews. If an examiner ever asks you why we can't just blast a raw 3 kHz voice signal straight out of an antenna without bothering to modulate it, you need to point them directly to the brutal, undeniable physics of antenna size. It always comes down to the math of radiation efficiency and wavelength. Here is our battle plan for this explainer. First, the antenna problem. Second, AM power arithmetic. Third, angle modulation in FM. Fourth, multiplexing and guard bands. And finally, digital modulation.
Starting right off with Section 1, the antenna problem.
Let's look at the standard quarter wavelength rule for antennas, where the height of your antenna needs to equal the wavelength divided by 4. This stark comparison shows exactly why piggybacking our low-frequency info onto a high-frequency carrier is non-negotiable. If you try to transmit a 3 kHz audio tone directly, the wavelength is the speed of light divided by that frequency, which gives you 100 kilometers. Divide that by 4 and you're looking at building an impossible 25-kilometer tall antenna. But shift that exact same information onto a 1 megahertz carrier and your required antenna shrinks to just 75 meters. That's an ordinary, totally practical broadcast mast.
Moving right along to Section 2, AM power arithmetic. Exam alert. This is where you can easily grab 5 or 6 guaranteed marks every single year, but only if you make these fundamental AM formulas completely automatic in your brain. AM is basically all about bookkeeping on the signal's envelope, figuring out how deep it dips and tracking exactly how much power it's eating up.
So the absolutely crucial point here is this specific formula. This measures your transmission efficiency, which we denote with the Greek letter eta. It calculates how much of your total transmitted power actually contains useful information, which, remember, lives entirely in your sidebands rather than just being burned on a dead-weight carrier wave. That mu you see right there, that's your modulation index.
Now, think about the shocking reality of that formula for a second. Even if you have perfect 100% modulation where your index mu is exactly 1, your maximum transmission efficiency hits a hard brick wall at just 33.33%. That means literally 2/3 of your transmitted power is completely wasted on a pure carrier tone that carries zero actual information. Both of your sidebands are saying the exact same thing twice while the carrier just sits there eating all your power.
And that massive power dissipation pitfall in standard AM, that is exactly why single sideband suppressed carrier, or SSBSC, was invented. By filtering out the carrier entirely and stripping away one of those redundant sidebands, you get a whopping 83% power saving compared to full AM at a modulation index of 1. Write this down because it's a classic exam statement question regarding transmitter power costs.
All right, on to Section 3, angle modulation and FM.
Look closely at the amplitude row right here. In FM, the carrier amplitude remains rigidly constant. And guys, this is FM's absolute superpower. Because noise almost exclusively attacks the amplitude of a signal, an FM receiver can simply clip the signal flat and throw all that noise right in the trash. It gives you a wildly superior signal-to-noise ratio. But check out that bottom row. There's no free lunch. You pay dearly for that crisp audio quality with a much, much larger bandwidth requirement.
So when you actually need to calculate that massive FM bandwidth on a test, Carson's rule is your go-to cheat code. For wideband FM, where your modulation index beta is greater than 1, the bandwidth is approximated by multiplying the sum of your frequency deviation delta F and your modulating frequency FM by 2.
For instance, if they give you a commercial FM signal with a 75 kHz deviation and a 15 kHz audio signal, just add them to get 90, multiply by 2, and boom, 180 kHz bandwidth. Easy points.
Let's hit Section 4, Multiplexing and Guard Bands.
Let's walk through the exact steps to solve a really classic 2023 exam trap. Frequency division multiplexing, or FDM, works by assigning each message its own unique carrier frequency, basically stacking them side by side. But to prevent crosstalk, you need empty space between them, known as guard bands. If a question asks for the minimum bandwidth of 10 signals at 4,000 Hz each, with 400 Hz guard bands, pay incredibly close attention. 10 channels only have 9 internal gaps between them. So, step 1, 10 times 4,000 is 40,000 Hz. Step 2, 9 gaps times 400 is 3,600 Hz. Add them up, and your total is 43,600 Hz. Whatever you do, do not fall for the trap of multiplying the guard band by 10.
Finally, Section 5, Digital Modulation.
Time to upgrade our pedestrian on a train analogy straight into the digital era. Instead of a smooth, continuous wave, our message is now a stream of binary ones and zeros. Make sure you know this matrix. It's your ultimate cheat sheet for comparing the big three: ASK, FSK, and PSK. Notice how phase shift keying, or PSK, offers the absolute best noise immunity and the lowest probability of error among these binary schemes. Plus, it achieves all this while maintaining a beautifully tight bandwidth equal to just 2 times the bitrate, unlike FSK, which demands extra bandwidth for frequency deviation.
Exam alert! You're going to see conceptual comparison questions on this. Standard binary PSK is fantastic, but it requires coherent detection. That means the receiver needs an exact, perfectly synchronized local copy of the carrier wave, which makes your hardware expensive and complex. Differential PSK, or DPSK, brilliantly solves this by encoding information purely in the difference between consecutive phases, totally ditching the need for a synchronized carrier. But remember the trade-off. It's going to cost you a 3 decibel penalty in your error rate compared to standard BPSK.
Seriously, pull out your phone and take a screenshot right now. This 60-second recall box holds every single critical analog M formula you absolutely must have memorized before you even think about walking into that exam hall. From your antenna height formulas to your modulation index limits, all the way to your multitone power additions. If you drill these until they become pure muscle memory, you are practically guaranteeing yourself a higher rank. So, with these core shortcuts in your back pocket, the real challenge begins. Which of these modulation techniques are you gonna master first to grab those easy points? And more importantly, how are you gonna adapt when exam boards inevitably start combining them to test your grasp on hybrid digital-analog systems? Focus your learning, build that muscle memory for the math, and go secure your rank. Thanks for tuning into this explainer, and happy studying.